So I will start this afternoon by doing some basic numbers or statistics. And that this is part 3, the thing I didn't do 2 weeks ago. I did articles and a little bit about simulation, but I would like to tell you a little bit about basic statistics, or just some small things about doing measurements. After this, we will go start with a lab intro. But basic statistics, what do we need to know here? It's really very basic stuff, but we are very often doing measurements. For example, when we do simulation, we want to measure things. So it's quite common that we get a lot of numbers and we don't maybe really know what to do with them. So we are just, I will just illustrate some good things, that is, how do you calculate the average and things like that. I was going to do this in a very practical way. We can do some experiment here. What's the delay if I want to send a packet to this IEEE server and back? And let's get some ping times. So if I want to ping IEEE here, it first gets translated to an IP number, and then I get some pings here. And I can see that, that's enough. It's the same IP number, but I get actually, I get all the different DNS names. Ooh, that was rather strange. It must be some kind of round robin. I've never seen that before. But it's the same server, it's the same IP number. So, and I get the time here, the last time. It's 134 milliseconds here. And the next time it measures the round trip time, it's 118 milliseconds, and so on. So we can see that it differs slightly depending on, that's my network at home here. So, and it's also inside my Linux virtual machine. So there are many possible disturbances for the packets here. But these are excellent numbers, and we have done our experiment here, and we actually want to put it in our results here now in our study. So how should we do it? Well, we can make tables, fill in. Quite often it's clever to have some kind of spreadsheet. And I think that's the most, makes most sense. So we can enter our measured values here. So we had 134 milliseconds, we had 118, 121, and 120, 120, 125. Yeah, we can do all here, 124, 124, and 122. That's the numbers we got before I pressed interrupt here. So things that are interesting to do with these are typically to calculate some stuff, and average. The average is kind of the most, very often the most common thing to calculate. And but also standard deviation is interesting. It tells you how all these values vary. But one of the more unusual things that I rarely see someone calculate is actually the standard deviation of the mean value, the average. And that's really useful when you do a lot of measurements. So what kind of formulas are these? Well, they are not so difficult. when you look at formulas and math, it looks complex, but it's not very often. So the average or the mean is simply the sum of all values divided by the number of values. Not so strange. Standard deviation is a little bit more complex. Then you need to first calculate the mean value, and then you take the distance. You calculate for each value, you calculate the distance to the mean. That's the deviation in some way. And to sum up all things, you do square it, sum it up, and then divide it by n. And quite common, you have n minus 1 here. I will not explain that. And to compensate for the squaring here, you do a square root in the end as well. So you get the same unit as the mean value or the values themselves. Yeah, the n minus 1 is when you do measurements and you don't know really the actual mean. You use a sample mean here, and then you're estimating the real mean by the calculated mean, and then you should have minus 1. That's deep statistics. I don't want to explain more. But this is a very useful thing. It tells you how much on average each value deviates from the mean value. So it gives you kind of variation metric. Well, the thing is that there is a very useful formula, yet one more, and that's the standard deviation of the mean value. This is the standard deviation of all samples, all the values we have entered. But when we calculate the mean, we get less variation, since this is an average value. If we have a variation in the actual values, the mean value will not vary as much. It will be more stable. So the standard deviation of this average we have calculated is much better than or tighter. And you can calculate it by taking the normal standard deviation and divide by the square root of the number of measurements. And this is really good because it means that if we do more measurements, we get a higher n and we get a lower standard deviation of the mean value. All the values have their own standard deviation. It's the thing it's the process we are measuring, and we cannot influence this one. But this one we can influence by doing more measurements, and we get a more accurate average value. So this is quite interesting to actually keep in mind. And this really tells you how accurate you have estimated the average here. So how do you do this? Well, a spreadsheet is really the simplest. Microsoft Excel or Google something, or I very often end up with OpenOffice and the Calc, LibreOffice Calc, I think it's called here. In all these, they use the same formula language mainly. So these should work in all spreadsheet programs actually. So you can calculate the average by average, standard deviation by STDEV, square root, SQRT, and it's also sometimes good to count the number of measurements in an area sometimes. So can we use these things now to compute something? Yes, I press equal sign. That means I want to start a formula. And then I just type average and start a parenthesis. I could also find the functions in some guide here or search around, but then I mark the whole area that I want to do an average in here. and then I finish with the ending parenthesis. So that's the simple way of just calculating the average of all these numbers. If you don't know spreadsheets, practice, because it's a really useful tool. Same for standard deviation. I just write the function name, mark the area here, and ending parenthesis, and then I can see that on average it varies approximately by 4 milliseconds up and down from the mean value. Very often a normal deviation, a normal spread is standard dev times 2, which means we have actually yeah, I can do that calculation times 2. It's approximately 8. So more than 90% of all our ping times would end up around a maximum of 8 milliseconds from this measured value, average here. That's what our standard deviation tells us. But how accurate is this average? Well, then we need to calculate the standard deviation of the mean value. And that was simply this value divided by the square root of the number of measurements here. So, oops, we can, we can just count them manually if we like. 1, 2, 3, 4, 13. So that would work. And then we see that our average values is accurate to, well, it has a spread of 1 plus minus 1, but double that, and you will get a good estimate of how much the average, how accurate is our average here. So I just write a note here that our average with 13 measurements are approximately 122, and this plus minus maybe 2.2 milliseconds, something. So that's how we can express the final value if we want to summarize the whole thing. So that would make sense. And then we use 2 times the standard deviation, which is fairly common. Since it's a bit random, you can find higher values sometimes. For example, we had 134 here. It doesn't fit within this range, but this covers like 95% of all our measurements. It should cover most stuff. If we want a more accurate average, then we can increase, then we can doing slightly more measurements here, and that should mean that we could get a tighter average estimate here. So let's see what happens if we can let's see, we can also plot these things. That's always nice if I remember how. We have separate measurements, so I'm not sure. It's usually the best is just to make maybe this kind of dots. I think sometimes it's meaningful with lines in between, but I don't think this is the case for our thing. It's not a continuous thing, it's discrete measurements. So we could use this bar graph or actually just dots. I think that makes most sense here. So yes, I can use a lot of fancy titles, but I will make it simpler here now. So this is our diagram. So we can see that it's something strange with the first one, maybe, and then it became more smoother. Can we explain this one? Well, maybe. I suspect that it's some warm up in the computer system here. Maybe some caches that needed to be filled or something. I'm not sure. But let's do some more. We do maybe 5 more or something and check what happens. Oh. And strangely enough, it's the first one is really slow here. No, it was not. So now we have some more. We have 120. 25, 32, 5. Oh, 21. Maybe that's enough. So can we see if this is any more accurate? We had 122 and 1.1 here. Let's adjust these formulas now. We need to extend the area here. I can just drag it. So now we get an average of very similar. And the standard deviation, we also need to check like this. And now we have more measurements, so we can use our count function here instead, maybe, and we tell it to count all these instead. And we notice that the average is about the same, standard deviation is about the same, but the standard deviation of the mean is slightly lower now. So we get a more accurate average estimate here. So, and how many did we have? I think we had like 20 rows, it says here. So we have, yeah. So now with 20 measurements, we actually are approximately, maybe we should say 123 and plus minus 1.6 or something. If we double the 1.7. So just an illustration that it's the more values we collect, the better average value we can calculate in the end. And the standard deviation of the mean tells us how good we have. Should we do double the number of measurements here, or are we satisfied? We can see on the standard deviation of the mean if it's enough or not. And this is very useful, actually, when we simulate things. Oh, let's see, can I do like this maybe? Oh. I think it updated. Great. Now we see, we had one very high, 132 here, yes. But this is actually quite interesting when we simulate, because we never know, are we done? You can simulate for 10 minutes and you don't know, is it good enough? But given that you can calculate these stuff, you can actually make an estimate of how accurate values do you have. Should we double the simulation time? Should we stop or continue? So it's a useful tool. Okay, I will put up this as an example on Canvas later as well. But that's really the most important thing about numbers I would like to tell you. Can I trust my values here? Well, whenever you do measurements, you should actually consider how you're doing it, the methodology. Should I do it inside my virtual Linux box here? Or maybe it's better to do the ping outside in my Windows here. Then I reduce maybe one source of error. And I'm doing this at home now. Maybe someone was streaming Netflix or something when I did the measurements. That can influence the result quite a lot. And the time of day, is it crowded on the internet at this time maybe, or something. So we have a mix of systematic errors, that is errors that show up in all our measurements, and simply more local errors. We are a bit more clumsy or mistaken, by mistake make some errors. And these can be quite hard to, we don't really know. You need to reason an argument that you have done a good job, really, and maybe someone believes you. Sometimes you can check with, I can try pinging the IEEE server from some other place and some other computer, and that might give me some information. Are there any special assumptions here? Well, yes, we actually know from the beginning how internet works. For example, when we do pings here, we know that we get 120 milliseconds. It's quite slow. Very often you get lower figures like 20 or 30. And we know actually as a fact that these values we get, they cannot be negative. So, for example, if we have an estimate in the end that the values are around 20 and plus minus 30 up and down, it's unrealistic. They cannot really be minus 10. So we can use that actually to make a better job. We have already some knowledge about the internet. We might, so we can actually use that to make a better, calculations as well. So yeah, that's some basic things about handling numbers, calculating averages and things like that. I think that's perfectly enough for this course, at least. So yes, thank you.